All right. Okay. So when we are doing counting outcomes, okay, first of all, there are going to be two ways we're going to do this, okay? When we are counting outcomes, this all has to do with probability, by the way. We are going, no. Okay, we're going to do two things. We're going to do the fundamental counting principle, okay? This is really simple, okay? And then we're going to do an outcome tree. Okay? And this basically shows all of the possible outcomes, okay? So let's start with how we would do an outcome tree, okay? Let's say I'm going to put a new page on here. All right, let's say that let's say you go on a field trip and you have a choice. You can either get, it comes with a box lunch which has ham, turkey, or cheese sandwich. Okay, then with that you can get an apple, banana, orange, or pear. Okay, and then, well, let's just see how many different combinations we can come up with. Okay, thanks, Ruby. All right, so in order to do this, the first thing we're going to do, you're going to pick one of these types of sandwiches. You're either going to get a ham, a turkey, or a cheese sandwich, and you're either going to get an apple, banana, orange, or pear. Okay, so what are the three choices for the sandwich? Okay, so we're going to say ham, we're going to say turkey, and we'll say cheese, and we'll abbreviate, okay? Now, with each one of these, okay, you can get a ham. What can you also get? For your second choice, you get what? An apple, a banana, an orange, or a what? Okay, now if you choose a turkey sandwich, what do you also get? You can get an apple, banana, orange, or pear. If you chose a cheese sandwich, you get apple, banana, orange, or pear. Okay? Each of these points to a different outcome. All right? So what that means, if I chose these two, what does that mean? I got a ham sandwich and a what? And an apple. What would this mean? Ham and a banana. Okay? Each of these would have a different outcome. Okay? And this would be, so each one of these is a separate outcome. Okay? So if the question was how many possible outcomes could you have by choosing one sandwich and one fruit, okay? How many would there be? How many would there be over here? There would be 12 total. And if you chose to abbreviate, okay, you would have okay. Each one of these would be a separate outcome, right? Every single one is different. So if I chose, for example, this one, what did I choose? A turkey and banana. Okay, turkey sandwich with a banana for fruit. Okay, does that make sense? That's how you use an outcome tree to show all of the possible outcomes. And this, what we would do right here is just say 12 possible outcomes. Okay, does that make sense? Okay, so let's say that okay, we can also choose the second part, and this is the really simple part. Okay, look at these numbers. Okay, how many? Okay, this was an outcome tree. We understand this. Okay, the fundamental counting principle. Okay, this is really simple. Okay, this is called the fundamental counting principle. Okay? And when we have the fundamental counting principle, Okay, what we do is we take the total outcomes from each one. Let's look back at this chart. Okay, how many choices did I have for my sandwich? How many choices did I have for my sandwich? 3. How many choices did I have for the fruit? Okay, so if I take these two and I multiply them, what did I come up with? Okay, is this the same as this? Now, sometimes it's not practical to make an outcome tree. Okay, and it's better to use a fundamental counting principle. Okay, for example, can I erase this? Does everybody have this? All right. Let's say that I wanted you to find, okay, on your combination locks that you have on your lockers, how many numbers are there? Does it go up to 39? Is it? I think it's 39. We'll just say it's 39. It's fine. Okay, so you can choose. Now, that includes what? Is 0 one of the numbers? Yeah, okay. So you have a lock, okay, and you can choose anything from 0 to 39. Okay? Now, if Carson was to go out and just try a random combination, do you think there's possible that he could get it right? But do you think, how many possible outcomes do you think there are? Well, let's see. Okay? First of all, how many possible numbers could that first one be? Not 39, because you include what? You include 0. So how many possible outcomes are there? There's 40. Now, does anybody's locker combination have the same number more than once? It can, right? I mean, technically, your locker could be 3, 3, 3, couldn't it? Could be. So how many choices would I have for that second number? 40. And how many would I have for that third number? Okay. So if I was to take these, now, if I wanted to make a tree, an outcome tree, it would be ginormous, okay? It would be, I mean, like, I couldn't even fit it. Okay, because, think about this. If I did, my first number could be what? Anything between what?
1.
I could have 0, 1, 2. And then my second number would have what? 0, 1, 2, all the way down to what? 39. Okay, this would be a huge. So would it make sense for us to make an outcome tree here? Absolutely not. So I'm going to go back and I'm going to take these 3 numbers. Okay, 40 times 40 times 40. What do you get? Someone do that. Way more than that.
6,400.
Way more than that.
64,000.
64,000. Okay. So Carson, you would have a 1 in 64,000 chance of getting that combination right.
What if I told you something and then what were we gonna bet on?
Did you know that you would have a better chance of going out there and just guessing that than winning the lottery?
Yeah.
Yeah, these lottery, because your chances of winning a lottery just by going and buying a random ticket are like 1 in millions, which is crazy. Shit. Okay. Now let's scale it down a little bit. Okay, let's scale it down. Yesterday, your worksheet talked about number cubes. What is a number cube? It's just a regular what? Regular die. Okay, and how many sides are on a die? 6. Okay, so if I wanted you to find the total possible outcomes for rolling a number cube twice, okay? If I rolled a number cube twice, would it make sense for me to use a tree, an outcome tree? I mean, I could. It wouldn't be ginormongomonious. It wouldn't be too huge. But what would make more sense for me to do? The fundamental counting principle. How many possibilities are there for the first roll? It can be anything between what? It could be a 1, 2, 3, 4, 5, or 6, right? No, that's 6. Okay. And then the second one could be anything between what? 1, 2, 3, 4, 5, 6, right? So how many possible outcomes would there be? 36 total outcomes. Okay, does that make sense? Please don't ask me that. All right. What if I'd said, Carson, you were flipping a coin yesterday, right? Let's say Carson flips 6 quarters at a time. Okay? How many possible outcomes could I have for those quarters? You said 12.
30. No.
Somebody see if you can figure it out. Think about this, okay? the easy way to think about it is you said 12 because you think 6 and there's 2 outcomes for each one, right?
They have to multiply by each other.
But it's not that simple. Why? Because how many outcomes could the first one be? 2. How many outcomes could the second one be?
Yeah.
So 2 to the 6.
Does that make sense?
So there's
Okay.
6.
So if I did this, what would that be? 64 outcomes. Okay. Now, just to prove that it's not just 12. Okay. Do you understand why it's 64?
Yeah.
Okay. So just to prove that, if I did this, the first one would have to be heads or tails, wouldn't it? That's the first coin. Okay. This is coin 1. Coin 2 would have to be what? Okay. This is coin 3. This would have to be what? Okay, is this going to start to get to be a really big tree? It is. Okay, but all of these are different, right? This one says the first coin was heads, tails, tails. Is there any other one that's heads, tails, tails?
Yes.
No, there's not. Okay, does that make sense? Does that make sense? Okay, so and you got to be kind of careful here. Okay, let's think about this. Let's say that there are 2 totally independent variables. In other words, let's say I roll a number cube and I flip 2 coins. Okay, and I don't want to make a tree. I want to use the fundamental counting principle to figure this out. What do you think the numbers I'm going to multiply here are? All I have to think about is outcomes. How many outcomes are there for a number cube?
54.
Everybody. Just don't jump ahead. How many outcomes for a number cube? 6. How many outcomes for 1 coin? How many for the next one? And what do I do with these numbers? Just multiply them. Okay, what's that going to be? 24 possible outcomes. Okay, I could make a tree out of this, couldn't I? And it wouldn't be that bad. Okay, now, let's just say, where you have to think about it, okay, let's just say your typical multiple choice question on a quiz or a test. How many choices do you have? 4, right? It's usually A, B, C, or D? Okay. So let's say you have 4 possible answers, multiple choice, A, B, C, or D. Okay, and let's say that there are 5 questions. Would this be as simple as multiplying 4 times 5, do you think? It wouldn't, would it? Look, for the first question, okay, this is question 1. How many choices are there? A, B, C, or D, right? Right? So for the second, for number 2, how many choices are there? A, B, C, or D? A, B, C, or D? A, B, and I'm only on what? I'm only on question 2.
So it'd be 4 times 4 times 4 times 4 times 4. 4 to the 10 times.
So think about this. How many different combinations of answers could I have? Well, let's see. Would it make sense for me to continue this tree? It's going to get really big, right? So this is basically, like you said, 4. How many choices for the first one? 4. How many for the second one? How many for the third one? How many for the fourth one? How many for the fifth one? Okay, and what is that? 4 to the 5th power? 1024. Okay. Would this be a possible combination? How many are like that? 1 out of how many? 1024. Okay. So if I said, what is the probability that someone chose A?
1 to 1,000.
Could I turn that into a percent? What would that be?
1 divided by 1,020.
Which is what? Someone with a calculator, do 1 divided by 1024. What is Ben, the
1024.
designated calculator boy?
9.765.
Okay, I just wanted to show you something. Read me, Ben, read me exactly what your calculator says.
Oh, I just messed it up.
Do it, 1 divided by 1,024.
9.76.
Hold on. We'll say 9.76 times,
No, oh, 10 to the negative 4.
okay. What is that?
Scientific.
That's scientific notation, isn't it? Do you know how to change that into a standard number? You remember that? What would that mean? I would move this decimal where? 4 to the left. 1, 2, 3, 4. Okay? Pretty small chance, isn't it? Okay? All right. Does that make sense how we do this? Okay. I will pass out your